And if I looked right, we finished with number 17. So let's number 17 we couldn't get to come out though, could we? Yeah, that was the one. Okay. So let's take a look at number 19. Summation from n equals 0 to infinity of x to the 5n over n factorial. And remember the first part of this was to look at for the instructions are to find the interval of convergence and if we use a ratio test, which is what this implies, then where it's less than one here is where we can find out where it converges. So we're going to do this. Got our limit as n goes to infinity. Then we plug in n plus 1. So we got x to the 5 times n plus 1 over n plus 1 factorial all over x to the 5n over n factorial. So that's equal to limit as n goes to infinity. Up on top, that would be x to the 5n plus 5, distributive property, and then n plus 1 factorial times, and then n factorial over x to the 5n. So that becomes x to the 5n times x to the 5 over n plus 1 factorial. Actually, let me write that out now. Put in room. It's 1 times 2 to all the way up to n times n plus 1. And n factorial is 1 times 2 all the way up to n over x to the 5n. The x to the 5n here cancels the x to the 5n here. The 1 times 2 all the way up to n cancels with the 1 times 2 all the way to the n down here. So we got limit as n goes to infinity of x to the 5th over n plus 1. Now the x to the 5th doesn't have anything to do with the n, does it? So I can put it out in front. And that gives us 1 over n plus 1. And what does that go to? 0. Yeah. And if our limit is equal to 0, then our radius convergence is infinity. So it's all real numbers. See if I can spot something a little bit different.
Would that be the kind of difficulty that would be on the test?
Yeah.
Okay. I don't want to go anything like what happened
last time. Yeah,
that
that.
was much. I lost more than halfway through.
Number 17 that hard?
I mean, if you want to look at the jumble mesh this looks like, it's pretty big. Yeah, it was bad. Also, since we couldn't figure out what to do.
Oh, we figured out what to do. We just didn't agree with the book. I don't remember it being horrible except for the fact that we didn't agree with the book. Yeah. But that's where we're trying to figure out the discrepancy. The book has another one in the next section that's really off too. And at first I'm thinking, Jesus, I forgot how to work these. And then I looked at the next one. The next one's right on target. And then I looked back down and it's like, no, the guy her after. They probably have their graduate students to them. And they make mistakes. Okay, so let's look up through, I don't know, like 31. See what looks different. Same. Kind of the same. This is one we looked at that we didn't do it geometrically. We did it using the ratio, and it still came up same answer. Let's do this one just for fun. Okay, so again, we want to find this limit. This will be -1 to the n plus 1 plus 1, because we're plugging in n plus 1 for n, x to the n plus 1 over 6 to the n plus 1, all over -1 to the n plus 1, x to the n over 6 to the n. So limit as n goes to infinity. That's -1 to the n plus 2, which is -1 to the n plus 1 times -1. And that's x to the n plus 1. That's x to the n times x to the 1. And then 6 to the n, I didn't hardly leave enough room, but I think I fit in there. Poor planning. Okay, this is -1 to the n plus 1, x to the n. Yeah, plenty of room. Now, the reason why I split that up kind of weird like that, I rewrote this down here, or up here, n plus 1 plus 1, which is n plus 1, and then a plus 1, that gives me n plus 2. And that's what this one gives me, right? If I go backwards. But I wrote it that way because I noticed I had a -1 to the n plus 1 down here. So then that will cancel with that. The x to the n's cancel. The 6 to the n powers cancel. -1 to the first power up there. X. 6 down below. Okay, what's wrong here? -1 to the n plus 1. -1 to the 1. X to the n, x to the 1. 6 to the n, 6 to the 1. Just seems too easy. The absolute value of x comes out there. And what we're left inside is a -1 over 6. And the absolute value of that is 1/6. So it goes to 1/6, doesn't it? Correct. Yeah, because there's no n to plug it into. That's just too easy. Okay. I guess, well, that's what they got. Now, again, a ratio test implies the 1 is the kind of the key place where it changes, where it converges, and so forth. And so this part right here, then we'll take our value less than 1 and figure the radius. But that's still, we still got to check the endpoints. So if I got 1/6, absolute value of x is less than 1, multiply by 6, and you get the absolute value of x is less than 6, which gives us -6 to +6. Okay, so the question is what's happening at the endpoints. X equals -6 and x equal +6. If I go back to my original function, I guess it's right there. -1 to the n plus 1. -6 to the n power. 6 over n.
Why do you have -6?
That's our endpoint. X equals -6. Assuming this is our original function, I should look back through. Is it? Okay. So n equals 1, infinity, and then we got -1 to the n plus 1. And we plug 6 in for x, so 6 to the n. They are over there, won't they? And then 6 to the n here. They will in both of them, actually. Because over here, at -6 to the n, I could rewrite that as -1 times 6 to the n power, 6 to the n, and n equals 1 to infinity, negative 1 to the n plus 1, and this would be negative 1 to the n, and 6 to the n, 6 to the n. I'll come back to this other one. So 6 to the n's cancel. And n plus 1 plus n, which is negative 1 to the 2n plus 1. Now 2n plus 1 is always an odd power. Not sure if that helps us. It diverges then, doesn't it? It doesn't approach anything. Because if that's always odd, this is a negative. This keeps getting smaller and smaller. Yes, that diverges. Just well, if I just think about it, which isn't always good. If I put 1 in there, 2 times 1 is 2, plus 1 is 3, negative 1 is negative 1. And if you put in 2 times 2 is 4, plus 1 is 5, negative 1 to the 5th is negative 1. So you just keep adding negative 1 over and over. And like you said, it goes to negative infinity. So it diverges. Which means parentheses on that side. Now, I think our other one probably does. No, it probably alternates. Because the 6 over n's cancel. And that leaves us negative 1 to the n plus 1. Converges, it'd be telescoping, wouldn't it? Sort of. Because, yeah, if it went back and forth, if I put a 1 there, it'd be positive, so that'd be 1. Next one would be a negative 1, then 1, then negative 1. That diverges, doesn't it? As you indicate, it goes back and forth. It doesn't go to 0. Because 1 minus 1 would give you 0, plus 1 would be 1, minus 1 would go back to 0, and then plus 1 would give you back to 1, minus 1 would take you to 0, and so forth. So, yeah, like you say, it just keeps going back and forth. So that diverges.
It diverges because they cannot go anything.
It diverges because it doesn't converge. Doesn't approach like zero.
Okay, so if it doesn't converge anything, then it has to diverge.
Right. But I wish I could say the rule. Let's see if they agree. Okay, since they recognize as geometric, the formula from geometric doesn't even consider the endpoints. So it does diverge on both sides. Okay, 23, let's see, 25. How can I say that's geometric? Let's see. Geometric is when you got number 2, the n power. So they treat that as a number. You could with the n and the -1. Then -1 would cause you to flip it. Not sure where that would head. I guess I'm so used to geometric being a number, but not a variable. But that converges and it's less than 1. So anything to the n power is geometric. That's the n power. They didn't do the geometric there. But there is nothing, no n except for the power. Maybe that's the difference. No n except for the power. I guess I could rewrite all of this as to the n power, right? Maybe. Interesting. Oh well. Ratio test works on all of them, so we've been seeing, so that's fine. It's probably enough of those. Okay, let's take a look at this one. This one says write an equivalent series with the index summation beginning at n equals 1. Okay, 45 n equals 0 to infinity. X to the n over n factorial. And the goal is we want it to be n equals 1 to infinity. We talked about that last time, how some of them weren't quite, starting at the right value according to the formula. Well, this goal here is to rewrite it. This one's pretty easy. If you plug 0 in, I'm going to have x to the 0 over 0 factorial plus If I plug in n equals 1, I'm going to have x to the first over 1 factorial. I plug in n equals 2. I got x squared over 2 factorial. Now I'm starting at 1 instead of 0, but I need a 0 factorial here because it has to be the same. So what could I replace the n with? N minus 1? Because if I put n equals 1 in there, 1 minus 1 is 0, and I have my original 0 factorial. Now the top part, the x to the n, I could replace this with n minus 1. Because if I put 1 in for the n, 1 minus 1 is 0. So this was n equals 0, this is n equals 1, this is n equals 2. If I plug in n equals 1, I'm going to get 1 minus 1 is 0, so I got x to the 0. 1 minus 1 is 0, so I got 0 factorial. If I plug 2 in, 2 minus 1 is 1, so that's x to the first. 2 minus 1 is 1, so I got 1 factorial. And if I plug in n equals 3, 3 minus 1 is 2, so I got x squared. And 3 minus 1 is 2 factorial, and so on. And I see that this gives me the same summation, doesn't it? The idea behind that is that you could then freely use this one or could use this one because they're the same. (47) is easy. I had to really think about this afternoon. Now this one starts at n equals 2, and I want to rewrite it. So it starts at 1. Well, if I start thinking about some possibilities, for n is equal to 2, if I put 2 in for n, 2 minus 1 is 1, so I'm going to have x the first, over 7 times 2 is 14, minus 1 is 13, factorial. If I plug in 3, 3 minus 1 is 2, so I got x squared, over 7 times 3 is 21, minus 1 is 20, factorial. And I don't need it, but if I plug in 4, 4 minus 1 is 3, so I got x to the third. 7 times 4 is 28, minus 1 is 27, factorial. Now over here, I need to have something, when I plug in n equals 1, I need to have something that gives me 13. Just like I plugged in n equals 2 here, and that gave me 13, didn't it? So what I do is, instead of 7n minus 1, I'm going to put variables there, like a n minus b, or plus b, with a plus. And that should equal to 13. I don't know what a and b are yet, but I do know n is 1. So this would be a plus b is equal to 13. Now for n equals 2, I'm going to have the same a and the same b. But now this should give me 20. Now if I plug 2 in for the n, I'm going to have 2a plus b equals 20. Okay, so now I can solve this system of equations. So a plus b is equal to 13, and I got 2a plus b is equal to 20. If I multiply the first equation by -1, then we get negative a minus b is equal to negative 13. 2a plus b is equal to 20. Negative a plus 2a is a. Negative b plus b cancels. Negative 13 plus 20 is 7. 7. Not that I can remember what I came up with this afternoon. But now I plug a back into one of these. And I get 7 plus b is equal to 13. Take that over, and b is equal to 6. And that's what I propose, that a is 7 and b is 6. Now we can check it real easy. If I come up here, what I'm saying is the bottom part is an plus b, and a we said was 7, so this would be 7n, and b is 6. Well, let's check it. If I plug in n equals 1, 7 times 1 is 7, plus 6 is 13. That gives me my 13 factorial. If I plug in my next n value, which is 2, 7 times 2 is 14, plus 6 is 20. That gives me my 20 factorial. If I plugged in n equals 3, 7 times 3 is 21, plus 6 is 27, which gives me that. So that works. Now the top part, I think is easier. I need it to be x to the first, x squared, x to the third. So this would be x to what? N. Because if I plug in n equals 1, I'm going to have x to the first, which matches that. If I plug in my next one, n equals 2, that gives me my x squared and so on. So this would be our answer. Questions on that one? Number 47. See if I did it the hard way. I never did look at this. Well, that's too easy. Just replace n with n plus 1. I like my method better. Yn plus 1. This was n equals 3, and you went to n equals 1. Would you plug in n plus 2? I don't know. This takes away you having to think about it too much. If you know it's linear, it's going to be of this form right here. Now, properties of functions defined by power series. If you got your power series up here with your radius convergence, then you can take the derivative of it. Now, specifically, the derivative applies to the x part. So notice the a sub n stays as a sub n. But here we got x minus something to a power, some number. So we take our power, put it out in front. This remains as is, and I'll lower my power by 1. Only thing missing is to multiply it times the derivative of what's inside the parentheses, right? But if you always have x minus c, power series form, the derivative of that is always 1. So that's why I left it off. Now our integration. If we're integrating that, well, looking at just the x part, we add 1 to our power. So that's where the n plus 1 comes from. And then we divide by our new power. And notice the a sub n just remains because we're integrating with respect to x. Okay. Now notice here. Here's our function. Notice what it starts with, n equals 0. The derivative, it changes to n equals 1. That's not a mistake. You increase it by 1. Okay? So, on number 49, for example, here's our original function with our series in there. And see how it went from 0, we took first derivative, and it changed to n equals 1. That's it. And then I go from the first derivative to the second derivative, and it changes to n equals 2. Okay, so we're right on track there. Look at 51. What do you see wrong there? Yeah, that should be n equals 1. This should be n equals 2. And about integration, what's integration say? Integration remains the same. N equals 0, n equals 0. So it had like 3 mistakes. This is the one I was going to show in class. I thought that was like, that's got 3 screw-ups in it. I'm not going to show that one. 49 is almost too easy to show. You see for the derivative, they take the power, put it out in front, and then they lower it by 1. Now this has got an extra 3 here, though. Where's that come from? The derivative. Yeah, derivative, what's inside the parentheses. That's a chain rule. Unfortunately, do they even indicate anything about chain rule right here? No, it's kind of it's like, you should have put something in there about that, but they didn't. And it could be that that's implied as you take the 1/3 out in front, and it's not really a chain rule. And I could see that also. Anyway, I'm not going to show those, but. And that's the end of 9.8. Let me stop the video and start it again. Shift F10.